the pristine waters of the Pacific Ocean suddenly turned eerie and vacant. At the Farallon Islands off San Francisco, a biological anomaly shook the marine scientific community to its core. A massive 5-meter-long female great white shark, a flawless biological masterpiece perfected over 400 million years of evolution, was patrolling her prime hunting grounds, rich with fat-heavy northern elephant seals. Suddenly, her internal sensory systems registered a presence. Within hours, this apex predator, along with every other great white shark in the region, initiated a panicked deep-water flight. They did not just swim away, they dived hundreds of meters into the abyssal zone and fled thousands of kilometers across the open ocean, abandoning their primary feeding sanctuary for an entire season. Why would the most feared predator on the planet willingly choose starvation over territory? The answer lies in the arrival of a pod of orcas, commonly known as killer whales. For generations, popular culture and sensationalized cinema have painted the great white shark as the absolute ruler of the seas. However, modern marine biology has uncovered a shocking ecological truth. Today, we will explore the fascinating science behind why great white sharks harbour an absolute evolutionary terror of orcas, diving deep into the physiological, behavioural and chemical mechanics that drive this unprecedented subaquatic displacement. The throne of the ocean belongs to a different creature entirely. If you want to uncover more deep-sea scientific breakthroughs with us, please take a brief moment to like this video and subscribe to our channel. Your support allows us to continue producing rigorous, informative science documentaries. Before we submerge into the complex anatomical comparisons of these ocean giants, please leave a comment down below sharing exactly where and at what local time you're watching this documentary from right now. We love seeing our global community of science enthusiasts connect from every corner of the world. Now, let us dissect the ultimate clash of marine titans. To truly comprehend why the great white shark retreats from the presence of killer whales, we must first perform a comprehensive anatomical audit of this ancient cartilaginous fish. Known scientifically as Carcharodon carcharias, the great white shark represents the absolute zenith of non-mammalian marine predation. Every structural component of its body is meticulously engineered by hundreds of millions of years of natural selection to locate, ambush, and destroy large marine prey. By examining its mechanical bite forces, its internal vascular heat exchangers, and its unparalleled array of bioelectric sensors, we can see why this creature was long considered the undisputed king of the world's oceans. We begin our anatomical investigation with the primary weapon of the great white shark, its jaw and dental apparatus. Unlike mammals whose jaws are fused directly to their craniums, the upper jaw of a great white shark is loosely suspended from the skull by a flexible arrangement of ligaments and cartilage. This specific structural layout, known as palatoquadrate suspension, allows the shark to completely protrude its entire upper jaw downward and forward during a strike. This protrusion drastically increases the gape of the mouth, allowing the animal to seize massive chunks of prey that would otherwise be impossible to grip. When we analyse the mechanical physics of a great white shark bite, the numbers are staggering. Biomechanical modelling data indicates that a large adult shark measuring approximately 6 meters in length can generate a maximum bite force exceeding 18,000 newtons. This immense pressure is directed through dozens of triangular serrated teeth that function exactly like razor-sharp steak knives. These teeth are not embedded into bone, but rather sit in a continuously regenerating conveyor belt system within the connective tissue of the jaw. When a tooth is dulled or lost during a violent hunting event, a replacement tooth moves forward to take its place within days. The combination of this mechanical leverage and razor-sharp serration allows the great white shark to slice through the dense bone, thick muscle, and heavy blubber of marine mammals with terrifying ease. However, the predatory success of the great white shark is not dependent solely on raw mechanical force. It relies equally on a highly sophisticated physiological modification within its circulatory system that separates it from the vast majority of cold-blooded fishes. Most sharks possess a body temperature that matches the surrounding water, which drastically limits their muscular efficiency in cold, deep oceanic environments. The great white shark, along with other members of the family Lamnidae, has overcome this environmental limitation through a specialized internal countercurrent heat exchange system known as the rete mirabile. The term rete mirabile translates from Latin as wonderful net, and its biological function is nothing short of miraculous. It consists of a dense, intricately interwoven network of microscopic arteries and veins located deep within the lateral swimming muscles, the stomach, and around the brain. When cold, oxygen-rich blood flows from the gills toward the internal organs, it passes directly alongside warm, carbon dioxide-rich blood that is travelling away from the active, hard-working core muscles. Because these microscopic vessels are packed tightly together, heat is transferred directly from the warm venous blood into the cold arterial blood before it can escape into the surrounding ocean water. This localized heat retention allows the great white shark to maintain an internal core temperature that can be up to 14 degrees Celsius warmer than the ambient seawater. This regional endothermy provides the shark with massive metabolic advantages. Warm muscles contract significantly faster and with far greater force than cold muscles, allowing the great white shark to execute explosive bursts of speed when launching an ambush attack from the deep. Furthermore, a warm stomach accelerates the digestion of dense animal fats, while a warm brain and heated retinas allow for rapid cognitive processing and sharp visual acuity when patrolling dark, frigid coastal waters. Yet even the most powerful jaw and the most efficient thermal metabolism are useless without the ability to locate prey across vast, trackless oceans. To solve this problem, the great white shark utilizes an extraordinary array of sensory organs that detect physical properties completely invisible to human beings. While its senses of sight, smell, and hearing are exceptionally acute, its most advanced hunting tool is its bioelectric detection system, which operates through specialized organs called the ampullae of Lorenzini. Visually, the ampullae of Lorenzini appear as hundreds of tiny dark pores scattered across the snout, around the eyes, and beneath the lower jaw of the shark. When we look beneath the skin, each individual pore opens into a long, slender, transparent canal filled with a highly conductive clear glycoprotein gel. This gel-filled tube terminates in a delicate bulb-shaped sac lined with thousands of microscopic sensory hair cells. These hair cells are connected directly to the central nervous system via the cranial nerves. The physical properties of the glycoprotein gel within these canals are highly advanced, acting as an exceptional biological conductor of electrical currents. When any living organism moves through the water, its muscles contract, its heart beats, and its gills exchange ions with the surrounding salt water. These basic physiological processes generate an incredibly weak, localized bioelectric field around the animal. As the great white shark approaches a living creature, these external electrical fields create a voltage differential between the surface pore on the shark's skin and the internal sensory bulb at the base of the gel-filled canal. The sensitivity of the ampullae of Lorenzini is mathematically profound. A great white shark can detect electrical gradients as faint as 5 nanovolts per centimetre. To put this extraordinary sensitivity into perspective, it is the equivalent of detecting the electrical field generated by a standard 1.5 volt flashlight battery connected to electrodes placed thousands of kilometres apart in the open ocean. This bioelectric sensory array allows the shark to navigate with pinpoint precision through pitch-black water, heavy fog, or thick mud. It can detect the hidden heartbeat of a flatfish buried deep beneath the coastal sand, and it can track the subtle, muscular contractions of a wounded seal swimming hundreds of meters away. In addition to this electrical sensing system, the great white shark possesses a lateral line system that detects mechanical vibrations and pressure changes in the water. Running horizontally along both sides of the shark's body from the tail to the head, the lateral line is a fluid-filled canal lined with microscopic sensory structures called neuromasts. Each neuromast contains a tiny gelatinous cupula that bends whenever low-frequency sound waves or physical water displacements wash over the shark's flank. This allows the shark to detect the precise direction and distance of swimming animals, effectively giving it a map of acoustic and physical movements occurring throughout its immediate aquatic environment. When we combine all of these anatomical features, the great white shark emerges as a truly formidable apex predator. It is a warm-bodied, highly intelligent killer equipped with 18,000 newtons of hydraulic jaw force, a perpetual supply of self-sharpening teeth, and a sensory suite capable of reading the literal electrical and mechanical signatures of life itself. For millions of years, this exact structural blueprint reigned absolute. No other creature in the sea possessed the physical tools necessary to challenge this biological masterpiece. Yet despite this terrifying array of evolutionary weaponry, the great white shark will instantly abandon its kingdom when faced with a predator that possesses an even more advanced anatomical design. To understand why the great white shark yields its territory to the killer whale, we must transition our scientific investigation from the domain of cartilaginous fish to the highly advanced anatomy of the ocean's grandest mammalian predator. Scientifically classified as Orcinus orca, the killer whale is not actually a whale, but rather the largest extant member of the oceanic dolphin family, Delphinidae. While the shark relies on ancient, highly honed sensory and physical systems, the orca brings an entirely different level of evolutionary engineering to the subaquatic battlefield. By examining the massive weight and structure of the orca skull, the extraordinary scale and complexity of its cerebral cortex, and the physical principles of its active echolocation system, we can begin to see how this marine mammal completely outclasses the fish in both physical power and cognitive strategy. We begin by examining the structural foundation of the orca's offensive power, its massive skull and skeletal system. Unlike the great white shark, whose skeletal structure is composed entirely of flexible, lightweight cartilage, the orca possesses a heavy, dense skeleton made of true mineralized bone. The skull of an adult orca is a monumental biological structure, frequently weighing hundreds of kilograms on its own. This skull is constructed from thick, interlocking plates of dense calcium phosphate, designed to withstand immense physical impact and absorb extreme mechanical stresses. The physical implications of a bony skull versus a cartilaginous skull are profound. Cartilage is an excellent material for flexibility and energy conservation during long-distance cruising, but it deforms under extreme structural loads. Bone, conversely, provides a rigid, unyielding anchor point for skeletal muscles. The massive temporal muscles of the orca originate along the large crests of its bony cranium and insert into a heavy, rigid lower jawbone. This solid mechanical lever system allows an adult orca to generate a crushing force that far exceeds that of a great white shark, with estimates suggesting compressive forces climbing toward an astronomical 50,000 newtons. Furthermore, because its skull is made of solid bone, an orca can use its entire head as a devastating battering ram, delivering high-velocity impacts capable of fracturing the cartilaginous skeletons of sharks or shattering the internal organs of large marine mammals without sustaining damage to its own central nervous system. Enclosed within this massive protective bony vault lies the true crown jewel of orca anatomy, its extraordinary brain. The brain of an adult orca is one of the largest and most complex neurological organs in the history of life on Earth, weighing up to an astonishing 6 kilograms. In comparison, the brain of a large great white shark is a simple, elongated structure weighing less than 40 grams, dedicated primarily to processing immediate olfactory and sensory inputs. When we analyse the internal architecture of the orca brain, the differences become even more striking. The cerebral cortex of the killer whale, which is the region of the brain responsible for high-level cognitive processing, problem-solving, social communication, and emotional regulation, is exceptionally large and highly developed. The degree of cortical folding, known scientifically as gyrification, is measured by the gyrification index. the orca brain exhibits a gyrification index that is significantly higher than that of the human brain. This means that within its large cranial space, the orca has packed an immense surface area of grey matter, containing billions of interconnected neurons. Furthermore, the orca brain possesses a unique structural feature known as an expanded paralimbic system. This region connects the emotional processing centres of the brain directly to the higher-level cognitive areas of the cerebral cortex. This anatomical development suggests that orcas possess an incredibly sophisticated capacity for complex emotions, deep social bonding, and self-awareness. It is this massive neurological hardware that allows orcas to operate not as instinct-driven solitary hunters, but as highly conscious, strategic, and adaptive intellectuals of the ocean. They're capable of assessing novel situations, learning new behaviours throughout their lives, and formulating complex multi-stage tactical plans that can change in real time depending on the movements of their prey. However, a massive brain and a powerful bony skull are only effective if the animal can navigate and perceive its environment with absolute clarity. While the shark reads the ocean through passive electrical receptors, the orca actively illuminates its surroundings using one of the most advanced physical sensory systems known to science, active acoustic echolocation. The physical apparatus for echolocation is located entirely within the forehead and nasal passages of the orca, sitting directly above its bony skull. The process begins when the orca draws air into its internal nasal cavities. Located just below the blowhole are specialized muscular structures composed of fat and connective tissue known as phonic lips or monkey lips. By forcing pressurized air through these phonic lips, the orca creates high-frequency acoustic vibrations. These vibrations are not produced by vocal cords, but rather by the mechanical clicking of these internal tissues snapping together. Once these acoustic clicks are generated, they travel forward through a large bulbous structure that forms the rounded forehead of the orca, known as the melon. The melon is a highly specialized organ composed of a unique mixture of low-density lipids and specific fatty acids. The composition of these lipids is not uniform throughout the organ. Instead, they are structured in precise concentric layers that create a natural acoustic lens. As the raw sound waves pass through the melon, the fatty layers alter the velocity of the sound, focusing the scattered acoustic energy into a tight directional beam of high-frequency sound waves that is projected forward into the water ahead of the animal. These focused sound waves travel through the aquatic medium at a speed of approximately 1,500 meters per second, which is nearly 4.5 times faster than the speed of sound in air. When this directional acoustic beam strikes an object in the water column, whether it's a school of fish, a rock formation, or a distant great white shark, the sound waves bounce off the target and reflect backward toward the orca as an acoustic echo. The returning echoes do not enter through the orca's external ear canals, which are evolutionary vestigial and completely closed. Instead, the reflected sound waves are captured by the thin, hollow bones of the orca's lower jaw. This lower jawbone contains a long, continuous channel filled with a specialized, highly resonant acoustic fat that possesses the exact same acoustic impedance as seawater. This alignment ensures that the returning sound energy passes from the water into the jaw fat without any loss of signal quality. The fat channel conducts the acoustic vibrations directly to the middle ear, the tympanic bulla, and into the inner ear, where auditory nerves translate the physical vibrations into neural impulses that are fired into the massive auditory cortex of the brain. The physical resolution of orca echolocation is staggering. The auditory processing centers of the orca brain can decode these returning echoes to create a highly detailed, three-dimensional mental map of the environment. This system is so precise that an orca swimming in pitch-black water or dense, murky coastal currents can determine the exact size, shape, distance, speed, and trajectory of an object hundreds of meters away. More incredibly, because high-frequency sound waves can penetrate soft tissues before reflecting off structures of different densities, the orca's echolocation functions exactly like a medical ultrasound. As an orca scans a great white shark from a distance, it does not just see the outer silhouette of the fish. It can look directly inside the shark's body, mapping the location of its skeleton, its internal organs, and specifically the exact size, density, and positioning of its massive oil-rich liver. This active, penetrating sensory capability provides the killer whale with a total, unilateral informational advantage, allowing it to plan and execute a flawless structural strike before the shark even registers the mammal's presence. To fully comprehend the psychological and tactical domination of Orcinus orca over Carcharodon carcharias, we must transition our scientific focus from individual physical anatomy to the realm of behavioral ecology. The ultimate outcome of any subaquatic confrontation between these two massive marine predators is not decided solely by jaw force or muscle mass. It is dictated by the profound contrast between the ancient, solitary instinct of the shark and the highly organized military-grade group dynamics of the cetacean. By examining how the solitary behavioral architecture of the great white shark leaves it highly vulnerable, and comparing it to the complex acoustic communication, generational tactical transmission, and three-dimensional flanking maneuvers executed by killer whale pods, we can see how a clash between these two animals is less like an animal fight and more like a coordinated military raid against a lone individual. We begin by evaluating the behavioral framework of the great white shark. The shark is an evolutionary marvel designed for individual efficiency. From the moment it's born, a great white shark receives no parental care, no training, and no protection. It enters the ocean as a fully autonomous solitary unit. Its behavioral matrix is governed by hardwired genetic programs and individual trial and error experience. When hunting large marine mammals, such as juvenile elephant seals or sea lions, the great white shark relies entirely on a solitary ambush methodology. It descends into the deep, dark contours of the coastal seafloor, using its dark grey dorsal coloration to blend completely into the substrate. It watches the surface silhouette of its target using its acute vision, calculates the trajectory, and then launches a singular vertical ballistic strike designed to inflict massive trauma and cause the prey to bleed to death. While this solitary strategy is devastatingly effective against isolated pinnipeds, it possesses a catastrophic evolutionary weakness. It lacks scalability and real-time adaptability. Because the great white shark operates entirely alone, its cognitive bandwidth is limited to its own immediate sensory inputs. It does not possess a mechanism to share tactical data, request operational assistance, or coordinate defensive perimeters with other members of its species. When multiple great white sharks gather at a highly concentrated food source, such as a whale carcass, they do not cooperate. Instead, they establish a rigid, linear dominance hierarchy based strictly on body length and sex. Their interactions are limited to ritualized non-verbal displays of aggression, such as tail slaps, parallel swimming and gaping jaws designed to drive rivals away. The shark is mentally locked in a solipsistic universe, incapable of conceiving a shared tactical objective. In stark, terrifying contrast, the killer whale operates as an organic component of a highly integrated multi-generational collective known as a pod. An orca pod is not a random collection of individuals. It is a complex matrilineal society bound by deep genetic, emotional, and cultural ties. The social architecture of a pod is built upon decades of shared knowledge, where calves spend their entire lives alongside their mothers, grandmothers, and aunts, absorbing a massive repository of non-genetic behavioral data. This cultural transmission is highly specialized. Different ecotypes of orcas around the globe possess entirely unique vocabularies, social rules, and highly specific hunting techniques that are passed down through generations exactly like human dialects and traditions. The primary operational tool that enables this social cohesion underwater is their highly advanced acoustic communication system. While the great white shark is completely mute, lacking any physiological apparatus to produce sound, An orca pod functions within a continuous, highly structured acoustic matrix. Orcas use their internal phonic lips to generate a vast array of underwater sounds, which marine biologists categorize into distinct clicks, whistles, and pulsed calls. The clicks are used for the active echolocation we examined previously, while the whistles and pulsed calls are utilized exclusively for social communication and real-time tactical coordination. Each individual pod possesses a unique acoustic signature, a collection of group-specific calls that sound entirely different from the vocalizations of neighboring pods. When a pod is patrolling the open ocean or tracking a target, these pulsed calls serve as a continuous, high-speed data stream. Through these acoustic signals, individuals can communicate their exact spatial coordinates, their emotional state, the discovery of potential targets, and specific operational commands across several kilometers of dark ocean water. The acoustic environment of a hunting pod is a symphony of real-time intelligence gathering, allowing the collective to maintain complete situational awareness even when individuals are separated by significant physical distances. When an orca pod encounters a great white shark, this acoustic communication allows them to transition instantly from a standard travel formation into a highly coordinated three-dimensional offensive formation that functions exactly like a specialized military squad. Because orcas are air-breathing mammals with immense aerobic capacities, they are not constrained by the same physiological limitations as a fish. They can utilize the entire water column, manipulating the three-dimensional physics of the subaquatic environment to completely neutralize the shark's sensory systems. The tactical execution of an orca raid on a great white shark is a masterclass in behavioral geometry. Once a shark is located via long-range echolocation, the pod does not rush forward in a disorganized frenzy. Instead, they divide into distinct tactical units with clearly defined operational roles. Using high-speed synchronized acoustic calls, the matriarch of the pod coordinates the approach. One group of orcas will intentionally position themselves directly within the horizontal plane of the shark's blind spot, which sits directly behind its caudal fin. By approaching from the rear, they completely bypass the shark's forward-facing vision and prevent it from executing its signature vertical ambush maneuver. Simultaneously, another group of orcas will swim high above the shark, silhouetted against the bright surface of the water, while a third group descends into the abyssal depths directly beneath the shark's belly. This synchronized deployment completely overwhelms the shark's sensory arrays. If the shark attempts to read the electrical field of its environment using its ampullae of Lorenzini, it is met with an overwhelming mass of moving mammalian tissue from multiple directions at once. The lateral line system of the shark, designed to detect low-frequency vibrations, registers a chaotic wall of water displacement as multiple 6-ton apex predators close the distance with absolute precision. As the perimeter closes, the flanking units execute a series of highly calculated non-lethal maneuvers designed to contain and disorient the target. They swim in tight, overlapping geometric circles around the shark, a technique known as corralling. By using their massive pectoral flippers and powerful tail flukes, the orcas create a localized vortex of highly turbulent micro-bubbled water. This artificial turbulence disrupts the laminar flow of water across the shark's pectoral fins, drastically reducing its hydrodynamic lift and making it highly difficult for the fish to steer or execute sharp, evasive turns. Throughout this entire containment phase, the orcas communicate continuously, exchanging rapid, short-pulsed calls to adjust their positions in response to every micro-movement the shark makes. If the shark attempts to turn to the left, a flanking orca is already positioned there to block its exit vector. If it attempts to dive toward the safety of the deep-sea floor, the deep-diving unit rises up to force it back toward the mid-water column. The solitary shark, accustomed to being the ultimate authority in its environment, suddenly finds itself completely isolated, structurally surrounded, and mathematically outmaneuvered in a three-dimensional cage of living, thinking, communicating mammalian muscle. It is this total systemic collapse of the shark's individualistic survival strategy, when confronted by an intelligent, communicative military unit that represents the true foundation of the fear we're investigating. To truly appreciate the scientific complexity of how killer whales defeat great white sharks, we must analyze a profound neurological and physiological vulnerability inherent to the entire design of cartilaginous fishes. This vulnerability is a specific physiological state known as tonic immobility. While the shark is an unparalleled biological weapon when swimming upright, its entire nervous system can be completely hijacked and shut down through a precise physical reorientation. By examining the precise neurological pathways that govern tonic immobility, the hydromechanical forces killer whales generate to trigger this state, and the fatal respiratory consequences that follow, we can see how the orca uses physics to turn the shark's own physiology against itself. We begin by breaking down the neurological mechanism of tonic immobility from a veterinary and neurobiological perspective. Tonic immobility is an unlearned involuntary reflex state characterized by a profound temporary paralysis and a complete dampening of response to external stimuli. It is a severe form of physical inhibition that occurs throughout many animal phyla, but in sharks it is uniquely absolute. When a great white shark is forcibly rotated along its longitudinal axis so that its ventral side faces upward and its dorsal side faces down toward the seafloor, a massive sensory conflict occurs within its central nervous system. This neurological collapse is centered primarily within the shark's vestibular system, which manages equilibrium, spatial orientation, and balance. The vestibular apparatus of a great white shark consists of 3 semicircular canals filled with a specialized fluid called endolymph, located deep inside its cartilaginous cranium. When the shark is flipped upside down, the sudden, unnatural inversion causes an extreme shift in the fluid dynamics of these canals, sending a massive, chaotic torrent of sensory signals through the cranial nerves directly into the brainstem. Simultaneously, the sudden shift in gravity affects the shark's internal organs, causing them to press heavily against its spine and deep musculature. This mechanical pressure activates a dense network of internal stretch receptors and baroreceptors. The brainstem, overwhelmed by the simultaneous conflict of extreme vestibular inversion and internal visceral shifting, misinterprets this data as a catastrophic bodily failure. To prevent system-wide shock, the shark's autonomic nervous system initiates an immediate massive surge in the production and release of internal neurotransmitters, specifically serotonin and endogenous opioids. This sudden chemical flood completely saturates the neural synapses of the brain, acting as a massive natural anesthetic. Within seconds, the shark's muscle tone completely dissolves. Its pectoral fins, which normally act as rigid, active hydrofoils for steering, become entirely limp and flaccid. Its eyes roll backward into its sockets, its respiration rate plummets, and its sensitivity to physical pain or external touch drops to near zero. The animal is not merely resting, it is trapped in a state of profound catatonic coma. Its conscious mind is completely disconnected from its musculature, leaving this 18,000 Newton apex predator entirely defenseless and paralyzed. The execution of this neurological shutdown requires a tremendous amount of physical force and mechanical precision, which brings us to the advanced hydromechanical strategies deployed by the killer whale. An adult orca does not simply swim up and try to wrestle a 5-meter great white shark into submission. Doing so would expose the mammal to the shark's devastating jaws. Instead, the orca utilizes the laws of fluid dynamics and its own immense kinetic energy to execute a high-velocity, non-contact hydromechanical strike. The tactical maneuver begins with an orca accelerating to speeds exceeding 45 km per hour. As the 6-ton mammal moves through the fluid medium, its large, streamlined body displaces a massive volume of water, creating a powerful, localized wave of high-pressure hydrodynamic energy directly ahead of its snout. The orca directs this localized pressure wave with pinpoint accuracy, targeting the midsection and pectoral fins of the great white shark. As the orca draws near, it executes a rapid, coordinated twist of its entire torso, swinging its massive tail fluke in a powerful lateral arc. This motion creates a secondary, highly concentrated underwater vortex. When this massive wall of focused hydrodynamic force strikes the flank of the shark, it delivers an immense turning torque that instantly overrides the shark's muscular control. Before the fish can stabilize its position, the orca closes the distance and uses its dense, bony snout or its powerful pectoral flippers to physically huck the shark, driving its body through a full 180-degree rotation along its longitudinal axis. Once the shark is successfully inverted, the orca immediately secures its target to maintain the state of tonic immobility. Using its heavy, cone-shaped teeth, the orca bites down firmly near the base of the shark's pectoral fins. This bite is not intended to sever tissue at this stage. Rather, it functions as a rigid clamp. By holding the inverted shark firmly in place, the orca ensures that the vestibular system of the fish remains completely disoriented, preventing the chemical flood of serotonin from subsiding and keeping the shark locked within its deep catatonic paralysis. With the shark successfully neutralized via tonic immobility, a secondary, completely fatal physiological process begins to unfold: mechanical asphyxiation. To understand why an inverted shark quickly suffocates, we must examine the specific fluid mechanics of its respiratory anatomy. Unlike many bony fishes that possess an operculum, a muscular bony flap that can actively pump water across the gills while the animal is stationary, the great white shark possesses 5 open, exposed gill slits on either side of its neck. Because it lacks an active pumping mechanism, the great white shark is classified as an obligate ram ventilator. This means that in order to breathe, the shark must maintain continuous forward motion through the water with its mouth slightly agape. As the shark swims, the forward velocity forces oxygen-rich seawater to continuously enter its oral cavity, travel through its pharynx, and ram directly through the delicate, blood-rich filaments of its gill arches before exiting through the lateral gill slits. This continuous passive fluid flow is the only way the shark can extract dissolved oxygen from the marine environment to sustain its highly demanding warm-bodied metabolism. When the killer whale flips the great white shark upside down and holds it motionless in a state of tonic immobility, this vital ram ventilation process stops instantly. Because there is no forward velocity, water stops flowing through the oral cavity. The static water trapped inside the gill chambers quickly becomes completely depleted of dissolved oxygen. Within the delicate gill filaments, the gas exchange process reverses its efficiency. Carbon dioxide builds up rapidly within the shark's bloodstream, a medical condition known as hypercapnia, while oxygen levels drop to near extinction levels, causing acute cellular hypoxia. As the minutes pass under this state of forced immobilization, the physiological damage escalates exponentially. The shark's warm, highly active metabolic systems require a continuous, heavy supply of oxygen to maintain cellular integrity. Without it, the heart muscle begins to fail, its contractions becoming weak and irregular. The highly folded brain, deprived of oxygenated blood, suffers rapid neurological degradation. The shark is caught in a perfect biological trap. It cannot move because its brain is paralyzed by tonic immobility, and it cannot breathe because it cannot move. The killer whale simply holds the shark upside down in the quiet depths, waiting patiently as the fish's internal systems systematically collapse from a total lack of oxygen, transforming the world's most feared cartilaginous predator into a completely motionless, suffocated mass of protein. Once the great white shark has been thoroughly incapacitated by tonic immobility and rendered clinically brain-dead through forced respiratory asphyxiation, the killer whale transitions from a tactical hunter into a highly precise biological surgeon. The post-mortem behavior of orcas targeting great white sharks is one of the most remarkable and chilling phenomena in modern behavioral ecology. Rather than consuming the entire carcass of the 5-meter fish, as one would expect from a massive predator, the orca executes a highly refined, localized dissection. It focuses its entire physical effort on extracting a single, specific internal organ, the massive lipid-rich liver, while leaving the rest of the muscle tissue, bone and skin almost entirely untouched. By examining the precise mechanical methodology behind this targeted extraction and analysing the unique biological proportions of the shark liver, we can understand the surgical precision of this apex cetacean. To appreciate the mechanical difficulty of this extraction, we must first look at the outer defensive armour of the great white shark. The skin of a shark is not smooth like that of a mammal, nor is it covered in loose scales like that of a bony fish. Instead, it is densely packed with millions of microscopic, tooth-like structures known as dermal denticles or placoid scales. These denticles are structurally identical to teeth, consisting of an inner core of dentine covered by a hard outer layer of vitrodentine. The sharp points of these denticles face backward, creating an incredibly tough, abrasive surface that feels exactly like coarse sandpaper. This specialized skin functions as a highly protective suit of chainmail, designed to resist punctures, tearing, and the bites of competing predators. To bypass this abrasive armored barrier, the killer whale utilizes its large interlocking conical teeth with extreme anatomical precision. The orca does not violently tear the shark apart at random. Instead, it targets a highly specific structural weakness located on the ventral side of the shark's torso, right between the two large pectoral fins. The orca approaches the motionless floating shark and positions its upper and lower jaws directly over the base of one of the pectoral fins. Using its massive jaw muscles, which are anchored firmly to its solid bony skull, the orca applies a highly calculated, concentrated compressive force. It does not bite to sever the entire fin. Rather, it uses its teeth to puncture the tough dermal denticles and grip the underlying skeletal cartilage of the pectoral girdle. Once a firm mechanical grip is established, the orca initiates a powerful, controlled lateral shaking motion of its head, utilizing the immense torque of its thick neck muscles. This specific twisting force creates a highly clean linear tear along the thin ventral wall of the shark's chest cavity, running horizontally between the pectoral fin attachments. This mechanical action functions exactly like an industrial zipper. Because the skin and underlying musculature are pulled under extreme tension, the single, precise tear opens up a massive surgical window directly into the shark's squelum, or internal body cavity. Because the internal organs of a shark are not anchored tightly by heavy, complex mesenteric tissues as they are in mammals, the sudden opening of this ventral window immediately exposes the internal viscera to the surrounding water column. The primary target of this surgical opening is the shark's liver, an organ that defies standard biological proportions. In terrestrial mammals and most bony fishes, the liver is a relatively small organ, typically accounting for less than 2 to 5% of the animal's total body weight. In the great white shark, however, the liver is a monumental biological structure. It is a massive bilobed dark bronze organ that dominates the entire internal anatomy of the animal. In a mature adult great white shark weighing approximately 1,200 kilograms, the liver alone can weigh anywhere from 250 to nearly 400 kilograms. This means that a single internal organ can account for an astonishing 25 to more than 30% of the shark's entire biological mass. From an evolutionary standpoint, the extreme size of the shark liver is an absolute structural necessity. Because sharks are cartilaginous fish, they lack a swim bladder, the gas-filled organ that allows bony fishes to maintain neutral buoyancy at various depths in the water column. Bone is highly dense and heavy, whereas cartilage is lighter, but a shark's massive muscles and internal organs still create a net negative buoyancy, meaning that if the shark stops moving, it will naturally sink straight to the bottom of the ocean. To counteract this constant downward gravitational pull, the great white shark relies on its enormous liver as a primary hydrostatic balancing mechanism. The cells of the shark liver, known as hepatocytes, are packed with vast quantities of low-density lipids and specialized oils. Because oil is significantly less dense than salt water, the massive volume of oil stored within the liver acts exactly like an internal, liquid-filled life jacket. This low-density organ provides the shark with near-neutral buoyancy, drastically reducing the energetic cost of swimming and allowing the animal to glide effortlessly through the water column, using its pectoral fins as aerodynamic wings. The orca, with its advanced active echolocation system, is fully aware of this internal anatomical layout. As we established previously, the high-frequency sound waves emitted by the orca can penetrate the soft tissues of the shark, returning an acoustic map that reveals the exact location, boundaries, and density variations of this massive oil-filled prize. Once the horizontal ventral incision has been successfully opened between the pectoral fins, the orca utilizes the natural physics of the marine environment to extract the liver cleanly. Because the liver is incredibly rich in light oils, it possesses high natural buoyancy. The moment the outer containment wall of the chest cavity is ruptured, the massive bilobed liver naturally begins to float out of the incision, separate from the heavier internal organs like the stomach and intestines, which remain anchored deeper within the body. The orca then gently pushes its snout against the shark's torso, or uses a highly controlled, localized suction technique created by rapidly expanding its oral cavity. This creates a low-pressure zone directly outside the incision, drawing the floating liver smoothly out of the shark's body. The orca then uses its teeth to neatly sever the hepatic ducts and blood vessels that connect the liver to the central circulatory system. The extraction is so mathematically clean that marine biologists who examine the remaining shark carcasses frequently report that the liver looks as though it was removed by a trained human pathologist using a surgical scalpel. The rest of the shark's body, including hundreds of kilograms of high-quality muscle meat, is simply cast aside, allowed to sink down into the abyssal depths to be consumed by deep-sea scavengers, crabs, and hagfish. To a human observer, this seems like an incomprehensible waste of biological resources. Why would a massive predator expend energy to hunt, track, paralyze, and dissect an 18,000 Newton killer, only to discard more than 70% of its body? The answer to this evolutionary mystery lies deep within the realm of marine biochemistry and molecular nutrition, which we will analyze next. To truly comprehend why the killer whale executes such a precise surgical dissection of the great white shark, we must transition our scientific investigation from macroanatomy to the specialized domain of marine biochemistry. The reason orcas selectively consume the liver while discarding hundreds of kilograms of high-quality muscle meat is rooted entirely in dietary energetics and molecular efficiency. The liver of a great white shark is not merely a buoyancy organ, it is a highly concentrated biochemical powerhouse. By examining the molecular architecture of the primary hydrocarbon compound stored within this organ, known as squalene, and analyzing the extreme density of essential vitamins and metabolic calories it contains, we can understand the exact nutritional mathematics that drive this targeted predation. We begin our biochemical analysis by looking at the specific molecular structure of the primary lipid found within the shark's liver cells. This compound is known scientifically as squalene. From an organic chemistry perspective, squalene is a naturally occurring organic compound classified as a triterpene. Its exact molecular formula consists of 30 carbon atoms and 50 hydrogen atoms. Structurally, it is a long branched hydrocarbon chain containing 6 double bonds, which classifies it as an unsaturated hydrocarbon. The physical and chemical properties of this 30 carbon, 50 hydrogen molecule are highly unique. Because it is a pure hydrocarbon with no highly polar functional groups, squalene is completely hydrophobic, meaning it is entirely insoluble in water. It possesses a remarkably low specific gravity, measuring approximately 0.86 grams per milliliter, which makes it significantly less dense than pure water and seawater. This low density is what provides the shark with its hydrostatic buoyancy, but for a warm-blooded mammalian predator like the orca, the value of this molecular structure lies entirely in its thermodynamic chemical bonds. When we evaluate the caloric density of different macronutrients, the differences are stark. Standard proteins and carbohydrates yield approximately 4 kilocalories of metabolic energy per gram. Standard animal fats and triglycerides, which are the primary energy storage molecules in most marine mammals, yield approximately 9 kilocalories per gram. Squalene, however, due to its highly concentrated hydrocarbon backbone packed with 30 carbon atoms and 50 hydrogen atoms, possesses an even higher chemical energy potential. When metabolized through cellular oxidation pathways, this unique hydrocarbon compound releases an astronomical amount of thermal and chemical energy, yielding nearly 10 kilocalories of energy per single gram. For an orca, maintaining homeostatic body temperature and powering a 6-ton muscular frame in freezing polar and deep temperate oceans is an extraordinarily expensive metabolic process. An adult killer whale requires hundreds of thousands of kilocalories every single day just to survive. If an orca were to consume the skeletal muscle meat of a great white shark, its digestive system would have to process high-density proteins composed of complex amino acids. Protein metabolism is highly inefficient. It requires a massive amount of internal water to process, produces toxic nitrogenous wastes like urea that must be filtered out by the kidneys, and exhibits a high thermic effect, meaning the orca would burn a significant portion of the consumed calories just trying to digest the tough muscle tissue. By contrast, consuming a 300 kilogram liver packed with pure squalene is the evolutionary equivalent of drinking pure high-octane liquid fuel. The long hydrocarbon chains of squalene are rapidly processed by the mammalian liver and digestive enzymes, bypassing the energy-taxing pathways of protein breakdown. A single shark liver can provide an orca with over 2 million kilocalories of immediately bioavailable metabolic energy. This extreme caloric density allows a hunting pod to maximize its foraging efficiency, obtaining days' worth of vital metabolic fuel from a single, short surgical extraction, rather than spending hours consuming and digesting an entire carcass. However, the biochemical wealth of the great white shark liver is not limited solely to its hydrocarbon energy content. The organ also functions as an unparalleled biological reservoir for critical micronutrients, most notably vitamin A and vitamin C. In the marine environment, vitamins are highly prized resources that cannot be synthesized internally by apex mammalian predators. They must be obtained entirely through the food web. Vitamin A, known chemically as retinol or its various esterified forms, is a fat-soluble vitamin that is present in the shark liver in massive, highly concentrated quantities. Because the liver cells are designed to store immense volumes of lipids, they naturally accumulate and concentrate fat-soluble micronutrients that travel up through the marine trophic levels. For the killer whale, a massive dose of vitamin A is a vital physiological requirement. This molecule is the primary building block for rhodopsin, the light-sensitive photopigment located within the rod cells of the eye. A steady, high-density supply of vitamin A ensures that the orca maintains exceptional visual acuity in low-light environments, allowing it to navigate and hunt in dark coastal waters or at extreme depths where sunlight cannot penetrate. Furthermore, vitamin A is essential for maintaining cellular integrity across the animal's vast skin surface, regulating immune function and protecting its internal mucous membranes from parasitic infections. Simultaneously, the shark liver contains surprising concentrations of vitamin C, known scientifically as ascorbic acid. While vitamin C is typically a water-soluble compound associated with terrestrial plant life, in the specialized biochemistry of marine apex predators, it accumulates within highly active metabolic tissues. For a marine mammal like the orca, vitamin C is a critical antioxidant resource. The immense muscular exertion required to propel a 6-ton body at high speeds creates a massive amount of oxidative stress and generates high levels of damaging free radicals within the animal's tissues. Ascorbic acid functions as a powerful reducing agent, donating electrons to neutralize these free radicals and protecting delicate cellular structures from oxidative damage. Additionally, vitamin C is an absolute requirement for the biosynthesis of collagen, the primary structural protein that forms the animal's thick connective tissues, its powerful tendons, and its specialized dermal layers. When we synthesize all of these chemical data points, the targeted hunting strategy of the killer whale becomes perfectly logical from an evolutionary and thermodynamic perspective. The great white shark liver represents the ultimate premium product in the oceanic marketplace. It is a massive 300 kilogram biocapsule filled to capacity with a unique hydrocarbon compound consisting of 30 carbon atoms and 50 hydrogen atoms, yielding maximum caloric returns with zero metabolic waste. It is simultaneously fortified with an elite concentration of fat-soluble vitamin A for deep sea vision and water-soluble vitamin C for systemic tissue repair. By executing a highly coordinated low-risk team maneuver to paralyze and asphyxiate the shark, and then deploying their teeth with surgical precision to open the ventral chest wall, the orcas gain access to a nutritional jackpot that completely outclasses any other food source in the ocean. They do not waste time or digestive energy on the tough, unbuoyant, protein-heavy muscle mass of the fish, because doing so would lower their overall foraging efficiency. They extract the lipid-rich prize, fuel their highly demanding mammalian metabolisms with pure calorie-dense squalene, and leave the discarded carcass behind. This is not random predation. It is highly advanced, biochemically driven ecological optimization practiced by the true intellectual sovereigns of the sea. To fully validate the unprecedented behavioral shift where the planet's premier predatory fish abandons its territory at the mere whisper of an orca's presence, we must step outside the realm of theoretical anatomy and examine the objective empirical evidence collected through the specialized field of marine telemetry. Telemetry, derived from the Greek words for distant and measurement, is the highly advanced scientific discipline of using specialized electronic transmitters to record and transmit data from wild animals across vast geographical spaces. In the trackless, opaque expanse of the global ocean, observing the real-time interactions between great white sharks and killer whales with the naked eye is statistically improbable. To overcome this environmental barrier, marine biologists utilize an elite array of satellite-linked archival tags and underwater acoustic receivers, constructing a continuous digital map of subaquatic behavior. We begin our technical exploration of telemetry by analyzing the primary instrument used to track the long-range movements of Carcharodon carcharias, the smart position and temperature transmitting tag, known scientifically by its acronym, the spot tag. The physical installation of a spot tag is a highly precise field procedure. Researchers safely capture a great white shark, carefully guiding it onto a specialized submerged hydraulic platform attached to a research vessel. The platform is raised, and a continuous stream of oxygenated seawater is pumped directly across the shark's gills to sustain its ram ventilation metabolism while it is temporarily out of the water. Once the shark is stabilized, marine scientists use specialized, non-corrosive plastic bolts to secure the spot tag directly to the leading edge of the shark's large dorsal fin. The location is selected with strict adherence to biomechanical principles. The dorsal fin is composed of dense structural fibrous tissue and lacks major blood vessels or nerve endings, ensuring the installation causes zero physiological distress or hydrodynamic drag to the animal. The electronic architecture enclosed within the rugged, pressure-resistant polyurethane housing of a spot tag is exceptionally advanced. The tag contains an integrated microprocessor, a highly sensitive internal thermistor for measuring ambient temperature, a pressure sensor for recording swimming depth, a saltwater switch, and a high-frequency radio transmitter. This saltwater switch is the critical gatekeeper of the system. It continuously measures electrical conductivity across two external metal nodes. When the shark is swimming completely submerged, the highly conductive saltwater bridges the nodes, keeping the radio transmitter locked in a dormant energy-saving state. The moment the great white shark rises to the surface and its dorsal fin breaks through the surface tension of the water into the atmosphere, the electrical conductivity across the saltwater switch drops to zero instantly. This break triggers the internal microprocessor, which immediately activates the high-power radio transmitter. The tag emits a series of ultra-high-frequency radio pulses directed upward toward the sky. These radio signals travel through the atmosphere and are captured by a constellation of satellites operating within the Argos system. The Argos satellite array consists of multiple polar orbiting spacecraft, orbiting several hundred kilometers above the Earth. As a satellite passes over the coordinates of the transmitting shark, it measures the slight changes in the frequency of the incoming radio pulses caused by the relative motion of the satellite, a physical phenomenon known as the Doppler effect. By applying complex mathematical algorithms to this Doppler shift data, the ground-based computers can calculate the exact latitude and longitude coordinates of the shark with a spatial accuracy down to a few hundred meters. This data is then uploaded to global scientific databases, providing a continuous multi-year record of the shark's oceanic migrations. However, spot tags possess a structural limitation. They can only transmit data when the shark actively breaks the surface of the water. To capture the complex, deep water behavioral patterns that occur when a shark is patrolling coastal hunting grounds, scientists deploy a secondary, highly advanced device known as a pop-up satellite archival tag, or PSAT. Unlike the bolted spot tag, a PSAT is attached to the dorsal musculature of the shark using a small specialized anchor dart made of biocompatible titanium. The PSAT is designed to remain with the shark for a pre-programmed duration, typically ranging from 6 months to an entire year. Throughout this period, the internal sensors of the PSAT continuously record data at high-frequency intervals, measuring ambient water temperature, precise hydrostatic pressure to track diving depth, and ambient light levels. The light data is highly critical. By analyzing the exact timing of dawn, dusk, and solar noon, scientists can use numerical geolocation models to estimate the shark's approximate position, even when it remains hundreds of meters below the photic zone. At the exact conclusion of the pre-programmed tracking period, a localized electrical current is triggered within the PSAT's connection module. This current initiates a rapid electrochemical reaction, intentionally corroding a small metal wire that anchors the tag to its tether. Once this wire breaks, the highly buoyant gas-filled housing of the PSAT detaches from the shark and floats directly to the surface of the ocean. The moment the tag breaks the surface, it activates its radio transmitter and uploads its entire stored memory archive of depth, temperature, and tracking data directly to the Argos satellite network, allowing scientists to download a complete, uninterrupted digital diary of the shark's hidden deep-sea life. While satellite tags are unmatched for tracking long-distance oceanic crossings, mapping the precise, fine-scale interactions within a specific coastal sanctuary requires a third telemetry methodology, acoustic telemetry. This system relies on a two-part physical infrastructure consisting of an internal acoustic transmitter and an expansive array of stationary underwater acoustic receivers. The process begins by equipping individual great white sharks with an acoustic transmitter, a small cylindrical electronic device about the size of a standard AA battery. These tags are either deployed externally via a specialized pole spear or surgically implanted directly into the column of the shark during brief research captures. Once activated, the acoustic tag emits a continuous series of high-frequency sound pulses, typically operating at 69 kHz. This specific frequency is selected because it sits far above the hearing thresholds of both sharks and most marine mammals, preventing the acoustic signals from altering the natural behavior of any organisms in the study area. Each acoustic pulse is uniquely coded with a distinct pattern of millisecond-long gaps, functioning exactly like a subaquatic digital barcode that corresponds to one specific individual shark. To capture these underwater acoustic barcodes, marine conservation organizations establish extensive arrays of stationary receivers, such as the VR2W receiver network, anchored permanently to the seafloor along coastal migration routes, underwater canyons, and seal colonies. An acoustic receiver is a self-contained, pressure-housed hydrophone system capable of operating autonomously at extreme depths for up to a year. As a tagged GreatWhiteShark swims through the coastal waters, the 69 kHz acoustic pulses emitted by its internal tag travel through the fluid medium. If the shark passes within a detection radius of approximately 500 to 800 meters of our anchored receiver, the ultra-sensitive internal hydrophone captures the sound waves. The receiver's internal computer decodes the unique pattern of the acoustic pulse, matching it to the specific ID number of that individual shark, and writes a digital logline directly to its internal flash memory. This logline contains the precise millisecond timestamp, the unique shark identification number, and the specific geographic coordinates of that individual receiver. When marine biologists periodically retrieve these receivers from the ocean floor and download the stored data packets, they can reconstruct a highly detailed, localized map of spatial and temporal habitat use. By analyzing these synchronized datasets across hundreds of receivers, scientists can determine exactly how many hours a shark spent patrolling a specific reef, its preferred depth contours, and its exact reaction when another tagged animal enters its immediate vicinity. It is this vast, unyielding network of digital eyes and ears, tracking the oceans from space down to the dark contours of the seafloor, that provided the empirical data necessary to uncover the true scale of the ecological terror we're exploring. When we apply the massive, multi-year empirical data sets gathered through satellite and acoustic telemetry to real-world ecological events, a stark, undeniable behavioral pattern emerges. This pattern is known in marine biology as the flight response, or spatial displacement profile of the great white shark. By analysing the precise tracking logs recorded during real-time encounters with killer whales, scientists have discovered that the flight of Carcharodon carcharias is not a standard, localised retreat. It is an immediate, absolute systemic evacuation. To understand the mechanics of this profound terror, we must analyse the specific telemetry records of these flight profiles, the biochemical properties of the chemical alarm signals that propagate through the water column, and the advanced spatial memory systems that keep the sharks in exile for months. We begin our analysis by reviewing the historic telemetry records that first revealed this phenomenon to the scientific community. At the southeast Farallon Islands off the coast of California, researchers had spent decades monitoring a dense, highly predictable population of adult great white sharks that gathered every autumn to hunt northern elephant seals. In October of 1997, a pod of transient killer whales entered the sanctuary, intercepted a 3-meter great white shark, and executed the classic hydro-mechanical inversion and surgical liver extraction we analysed previously. The telemetry data recorded from the remaining sharks in the area immediately following this single predatory event was staggering. Every single acoustic transmitter tag in the region registered an immediate, simultaneous spike in swimming velocity away from the islands. Within a mere 3 to 6 hours of the Orca attack, the entire local population of great white sharks had completely vanished from the Farallon Islands. The data logs from the anchored acoustic receivers showed that the sharks did not merely retreat to deeper coastal waters a few kilometers away. They entered a high-speed direct flight path heading straight out into the open, deep-sea expanse of the Pacific Ocean. Many of these individual sharks swam over 3,000 kilometers toward a remote oceanic region, situated halfway between California and Hawaii, known colloquially by marine biologists as the White Shark Cafe. More remarkably, the telemetry records show that not a single tagged shark returned to their prime coastal hunting grounds for the remainder of that entire annual feeding season. To explain how an entire population of apex predators can detect an event occurring at a single point in space and initiate a synchronized, frantic flight within hours, we must look at the highly advanced olfactory anatomy of the shark and the physical chemistry of chemical alarm signals, known in behavioral ecology as Schreckstoff or necromones. The great white shark possesses one of the most sophisticated olfactory systems in the animal kingdom. Its snout contains two large forward-facing nasal cavities that are entirely separate from its respiratory system. As the shark swims, water is continuously forced into these cavities and directed across a series of highly folded, blood-rich structural membranes known as olfactory lamellae. These lamellae are lined with millions of specialized chemoreceptor cells that are connected directly to the massive olfactory bulbs of the brain, which account for nearly 18% of the shark's total neurological mass. This system is so sensitive that a great white shark can detect specific chemical compounds dissolved in seawater at a concentration of less than 1 part per 25 billion. When an orca breaks open the ventral chest wall of a great white shark to extract its liver, a massive cloud of internal chemical compounds is instantly released into the surrounding water column. This chemical cloud is packed with specific biochemical indicators of mortality, including decayed lipids, ruptured blood products, and specific dense putrefaction compounds such as putrescine and cadaverine. Together, these compounds form a highly potent necromone. The propagation of this necromone through the marine environment is governed by the laws of fluid dynamics, driven by tidal currents, coastal upwelling, and molecular diffusion. Because the ocean is a dynamic, moving fluid, these chemical molecules spread outward from the kill site, creating a long, concentrated underwater plume of warning signals. As neighbouring great white sharks patrol the region, their continuous forward swimming forces this water into their nasal cavities. The moment these specific necromone molecules bind to the chemoreceptors on the olfactory lamellae, a massive immediate threat response is triggered within the central nervous system. The neurological pathway of this chemical alarm avoids all higher-level cognitive processing. The sensory signals from the olfactory bulbs bypass the forebrain and fire directly into the amygdala and the hypothalamus, the ancient evolutionary centres responsible for survival and the fight-or-flight reflex. The immediate result is a massive, uncontrollable surge of adrenaline and stress hormones throughout the shark's bloodstream. The shark's heart rate spikes, its metabolic system shifts into overdrive, and its behavioural programming completely overrides all hunting or territorial drives. To the shark's brain, the scent of its own species' ruptured flesh is an absolute biological red line indicating the presence of an unstoppable, existential threat. The animal turns away from the chemical plume and flees at maximum speed. However, the chemical plume itself is temporary, typically dissipating within a few days as coastal currents dilute the necromone molecules below the detection threshold. This raises a fundamental scientific question. If the chemical warning disappears within 72 hours, why do the telemetry records prove that great white sharks remain in exile, refusing to return to their hunting grounds for up to a year? The answer lies in the complex spatial memory and cognitive mapping systems housed within the shark's brain. While popular culture often mischaracterizes sharks as mindless, instinct-driven automatons with short memory spans, neurobiological research has proven that Carcharodon carcharias possesses an exceptionally advanced long-term memory system. This cognitive architecture is centered within the telencephalon and the hippocampal formations of the shark brain, regions that are highly developed in wide-ranging apex predators. The great white shark relies on this spatial memory to construct a highly complex, multi-layered cognitive map of the global ocean. Throughout its decades-long lifespan, a shark memorizes the exact geographic coordinates, seasonal thermal profiles, and prey densities of multiple far-flung coastal sanctuaries. They know precisely which underwater reefs host the highest concentration of fat-heavy juvenile seals at specific times of the year, and they synchronize their multi-thousand-kilometre migrations to arrive at these exact coordinates with mathematical precision. When a single, catastrophic predatory event disrupts this cognitive map, such as the arrival of an orcapod and the subsequent death of a fellow shark, the event is permanently seared into the animal's long-term neurological memory. The brain associates those specific geographic coordinates, those precise reef contours, and that specific seasonal time frame with absolute near-fatal danger. This cognitive association creates a powerful behavioral phenomenon known as the landscape of fear. The shark's spatial memory operates as a risk assessment engine. It continuously weighs the potential caloric benefits of a hunting ground against the perceived statistical probability of mortality. Even though the physical presence of the orcas may have been brief and the chemical necromones have long since washed away, the shark's internal cognitive map continues to flag that specific region as a high mortality zone. The memory of the terror overrides the biological urge of hunger. The shark willingly chooses to remain in the barren, calorie-poor open ocean, navigating along completely alternative migration routes for hundreds of days, rather than risking a return to a compromised kingdom. This is not a brief, knee-jerk reflex. It is a sophisticated, memory-driven survival strategy that reshapes the entire spatial distribution of the ocean's largest predatory fish. To fully appreciate how the theoretical and biochemical mechanics of this marine conflict manifest in the real world, we must narrow our scientific lens and examine a specific geographical epicenter that has rewritten the textbooks on marine behavioral ecology. We transition our investigation to the temperate coastal waters of South Africa, specifically focusing on the expansive marine ecosystems of False Bay and Gansbaai. Historically, this region represented the undisputed global capital of Carcharodon, Carcharias. For decades, thousands of adult great white sharks congregated here annually, patrolling the narrow, deep channels surrounding massive fur seal colonies such as Seal Island. This predictable concentration made South Africa the premier global destination for shark researchers and ecotourists alike. However, starting in the year 25, this ancient ecological equilibrium was systematically shattered by the arrival of just two extraordinary mammalian individuals. These two mature male killer whales are known to the global scientific community by the names Port and Starboard. Discovered and documented by South African cetacean researchers, these two animals are easily identifiable by a rare, highly distinct anatomical anomaly. Their massive 2-meter-tall dorsal fins are severely collapsed. The dorsal fin of Port is completely bent over to the left side of his body, while the dorsal fin of Starboard is collapsed entirely to the right. From a physiological standpoint, a collapsed dorsal fin in wild adult male orcas is an exceptionally rare occurrence, typically affecting less than 1% of wild populations. It occurs when the dense, structural collagen and fibrous tissue that keeps the fin erect weakens due to physical trauma, structural stress, or a prolonged shift in swimming orientation. However, what truly makes Port and Starboard a subject of intense scientific fascination is not their collapsed fins, but their highly anomalous, specialized behavioral profile. Marine biologists categorize these two males as a distinct, specialized subgroup of transient mammal-eating killer whales. Unlike resident orcas that travel in large, stable family pods consisting of dozens of individuals and specialize in hunting schools of fish using synchronized sound arrays, Port and Starboard operate primarily as a highly coordinated semi-autonomous pair. They are nomad hunters, patrolling thousands of kilometers of the rugged South African coastline with absolute stealth. The predatory behavior displayed by Port and Starboard represents a profound departure from standard orca ethology. While transient orca pods around the globe are famous for hunting marine mammals such as sea lions, harbour porpoises and juvenile baleen whales, Port and Starboard have developed a highly specialised hyper-targeted niche. They are dedicated shark specialists. More importantly, they have completely mastered the complex hydromechanical inversion and surgical liver extraction techniques that we explored in the previous sections of our documentary. When we observe the movement data collected from this predatory duo, their efficiency is nothing short of terrifying. Port and Starboard do not hunt at random. They utilize the specific coastal topography of South Africa to systematically trap their targets. False Bay and Gansbaai are characterized by unique underwater geomorphology, featuring steep, rocky headlands and shallow, sandy bays that create natural maritime funnels. Great white sharks enter these shallow bays to intercept young Cape Fur seals that are learning to navigate the crashing surf. Port and Starboard utilize these shallow contours as an active tactical advantage, operating in complete acoustic silence, suppressing their standard social whistles and pulsed calls to avoid alerting the highly sensitive lateral line and bioelectric systems of the sharks. The two male orcas enter the bays from the deep ocean. They coordinate their positions perfectly, swimming parallel to each other to block the deeper escape routes leading out to the open sea. By doing so, they intentionally herd the individual great white sharks into shallower water, compressing the shark's operational space and making it impossible for the fish to execute a rapid vertical dive into the deep water column. Once a specific great white shark is trapped within the shallow near-shore zone, Port and Starboard execute their synchronized strike with military precision. Because an adult male orca can weigh over 6,500 kilograms and measure up to 9 meters in length, both Port and Starboard are significantly larger and heavier than even the largest adult female great white sharks in the region, which rarely exceed 1,500 kilograms. This massive size differential provides the mammalian pair with an overwhelming physical and kinetic advantage. Starboard will typically initiate the primary offensive maneuver, using his massive body to generate a high-velocity hydrodynamic pressure wave that disorients the shark. Simultaneously, Port utilizes his immense speed to close the distance from the rear, striking the shark's flank with his solid bone snout to trigger the immediate 90-degree tilt. Together, using their interlocking teeth, they clamp onto the shark's pectoral fins, flip the 5-meter fish completely flat onto its back, and hold it down against the shallow, sandy substrate. Within seconds, the neurological trap of tonic immobility engages, and the shark's muscle tone dissolves into complete paralysis. Port and Starboard simply hold the heavy fish motionless in the breaking surf, waiting for hypercapnia and cellular hypoxia to completely drain the shark of its conscious life. Once respiration has ceased, they execute their surgical bite directly between the pectoral fins, tearing open the ventral musculature and allowing the massive, highly buoyant, oil-rich liver to float cleanly out of the body cavity. What makes the case of Port and Starboard so scientifically monumental is the sheer frequency and scale of their hunting operations. Throughout 27 and 28, researchers began discovering the dead carcasses of multiple large great white sharks washing up on the beaches of Gans Bay. When marine biologists performed detailed necropsies on these animals, they found the identical, flawless surgical signature of Port and Starboard, a clean, horizontal tear between the pectoral fins and a total absence of the massive liver, while the rest of the high-protein muscle tissue remained entirely untouched. The geographical impact of this targeted predation was immediate and catastrophic for the local ecosystem. The telemetry data showed that the moment Port and Starboard entered False Bay or Gans Bay and executed a single shark kill, the chemical alarm signals, the dense necrotic plume of squalene and decayed lipids, propagated rapidly through the coastal current systems. Within hours, every remaining great white shark in the entire bay initiated a high-speed, panic-driven flight response, abandoning the premier hunting grounds of South Africa. By tracking the presence of Port and Starboard through coastal sightings and acoustic receiver logs, marine scientists confirmed a direct mathematical correlation. Whenever the two male orcas arrived, the great white sharks completely vanished from the region for months at a time. The ancient sovereigns of the South African oceans, who had ruled these coastal waters for millennia, had been completely displaced by a single, highly specialized pair of nomadic mammalian intellectuals. The geographical profile of South Africa's marine apex predators had been fundamentally altered, providing scientists with an unprecedented look at how just two individuals can rewrite the ecological rules of an entire coastline. To establish indisputable empirical proof of the surgical methodologies used by Port and Starboard, we must examine the forensic evidence collected during the biological autopsies, or necropsies, performed on the great white shark carcasses that washed ashore along the western cape of South Africa. Led by pioneering marine biologist Alison Towner and a team of veterinary pathologists, these examinations provided the critical anatomical data that confirmed how a mammalian predator could systematically defeat the ocean's most feared fish. By looking closely at the precise tearing patterns on the skin, the targeted damage to internal structures, and the sudden, complete collapse of the regional shark population, these forensic reports offer a clear picture of this ecological shift. When a dead great white shark is discovered on a beach, time is of the essence. Pathologists must transport the multi-ton carcass to a controlled facility, or perform an immediate field necropsy before scavenging birds, terrestrial predators, or natural decomposition can destroy the delicate tissue markings. The first step in any scientific necropsy is a meticulous external inspection, mapping every tear, scrape, and puncture across the shark's skin. In the specimens recovered from the beaches of Gansby and Hermanus, the external inspections revealed a highly consistent chilling pattern. The primary physical evidence was not a series of chaotic, random lacerations, but rather a single, highly localized zone of trauma situated on the ventral side of the shark, right between the pectoral fins. The skin in this specific region was completely ruptured, showing a clean horizontal tear that exposed the underlying coalomic cavity. When pathologists examined the edges of this horizontal tear under magnification, they found clear evidence of extreme mechanical compression. The tough dermal denticles, which normally form a rigid protective suit of armour, were crushed and pushed inward. Deep teeth impressions matching the size, shape and spacing of adult male orca teeth were embedded into the thick collagen layers at the base of both pectoral fins. These puncture marks did not show the chaotic sliding or slicing patterns that would occur during a violent, prolonged struggle. Instead, they were deep, static impressions, indicating that the orcas had applied a massive, steady clamping force to the fins, holding the shark firmly in place while it was upside down. As the team dissected deeper into the wound, the internal findings became even more scientifically fascinating. The primary target of the necropsy was to evaluate the internal organ cavity. In every single carcass linked to Port and Starboard, the massive bilobed liver was completely absent. More significantly, the internal blood vessels, including the hepatic portal vein and the major hepatic arteries, were cleanly severed at the exact base where they join the central circulatory system. The surrounding internal organs, such as the muscular stomach, the long intestinal tract, and the spleen, were entirely intact and completely undamaged. The stomach was frequently found packed with the remains of recently consumed seals, proving that these sharks were healthy, active predators in the prime of their lives immediately before the attack. The clean nature of this internal trauma provided key insights into the physics of the extraction. If the orcas had simply bitten into the centre of the shark's belly and pulled, the stomach and intestines would have been torn out along with the liver. The fact that only the liver was missing proves that the orcas used a highly calculated technique. By clamping onto the pectoral fins and pulling outward in opposite directions, the mammals placed the ventral skin under immense tension. The skin split along its natural structural grain line, and because the liver possesses high natural buoyancy, due to its dense accumulation of squalene oil, it naturally separated from the heavier internal organs and floated smoothly out of the open incision. The orcas then used their teeth like surgical forceps to pinch and break the primary blood vessels, cleanly releasing the oil-rich prize. While the physical evidence on the dissection table was conclusive, the broader ecological data gathered from the surrounding waters revealed an even more profound consequence. The forensic verification of these shark kills directly matched the sudden, total disappearance of the local great white shark population from their traditional South African sanctuaries. Prior to these necropsy records, Fulspay and Gansby hosted stable populations of great white sharks throughout the year. Ecotourism vessels and research boats recorded dozens of individual shark sightings every single day. However, As the forensic team continued to document more surgically dissected carcasses washing ashore, the regional tracking databases registered a catastrophic drop in shark activity. The data collected from the extensive network of anchored acoustic receivers along the coast showed a total systemic shutdown. The moment a shark carcass was deposited on the beach, indicating a kill had occurred just offshore, every other tagged great white shark in the entire bay initiated a high-speed direct flight path away from the coast. The receivers, which normally recorded thousands of acoustic pings daily as sharks patrolled the seal colonies, went completely silent. Within days of an attack, the number of shark detections dropped to 0. This disappearance was not a temporary flight lasting a few days or weeks. The forensic tracking proved that the sharks remained in total exile for months, and in some cases, for over a year. Entire coastal bays that had been dominated by great white sharks for thousands of years were left completely vacant. The cage diving industry collapsed, research projects were forced to relocate, and the coastal waters became completely devoid of their primary apex predator. To understand why this disappearance was so absolute, we must look at how the physical evidence from the necropsies relates to the chemical warning signals we analysed earlier. The clean tear in the shark's chest wall did more than allow the liver to float out. It allowed a massive amount of internal blood, tissue fluids, and hepatic oils to pour directly into the coastal current systems. Because Gansby and False Bay are characterised by powerful swirling tidal currents, this dense cloud of death was rapidly distributed throughout the entire coastal zone. For a living great white shark, swimming into this concentrated plume of its own species' ruptured tissue is the ultimate sensory nightmare. The massive olfactory bulbs in the shark's brain register an extreme threat, triggering an immediate survival response that overrides all territorial fidelity. The physical evidence found during the necropsies, the crushed denticles, the clamped fins, and the missing livers, was the direct source of the chemical terror that drove an entire population into deep-water exile. The sovereign fish of South Africa had not merely been out-hunted, their traditional kingdoms had been rendered completely unlivable by the intelligent, calculated tactics of two extraordinary mammalian killers, leaving a vacant ecological throne that would quickly trigger a massive, unpredictable chain reaction throughout the entire marine environment. The total long-term displacement of Carcharodon carcharias from its primary coastal sanctuaries does more than prove the tactical superiority of the killer whale. It initiates a profound ecological phenomenon that ripples through every level of the marine food web. In environmental science, this systemic disruption is known as a trophic cascade, and its primary behavioral driver is a concept called the landscape of fear. Historically, scientists believed that predators only influenced ecosystems through direct mortality, by physically killing and consuming their prey. However, modern behavioral ecology has proven that the psychological impact of a predator, the continuous, localized fear of being hunted, exerts an equal, if not greater, regulatory force on the architecture of an ecosystem. By analysing how the sudden absence of the great white shark alters the behavioural topography of its prey, we can track the catastrophic environmental chain reactions that follow. To understand this ecological shift, we must first define the landscape of fear within the context of the South African marine environment. Before the arrival of the specialised Orca pair, Port and Starboard, the coastal waters of False Bay and Gansby were defined by a highly structured map of risk. The Cape fur seals, known scientifically as Arctocephalus pusillus, do not move through the ocean at random. They are fully aware that the deep, narrow channels surrounding their rocky breeding colonies are populated by large numbers of patrolling great white sharks. This continuous predatory presence creates a highly defined zone of extreme risk, forcing the seals to alter their entire behavioural profile. To minimise the probability of a fatal vertical ambush from the deep, the seals exhibit high spatial vigilance. They restrict their foraging trips to specific times of day, travel in large, tightly coordinated groups to maximise the number of eyes looking for danger, and navigate along highly specific, shallow topographical pathways where a shark cannot easily launch an underwater attack. This psychological pressure effectively keeps the seal population in check, preventing them from overexploiting their own food resources and maintaining a delicate balance within the coastal kelp forests. The moment the great white sharks flee the region to escape the threat of orca predation, this landscape of fear completely dissolves. The coastal waters, once a high-risk zone filled with unseen apex predators, are suddenly transformed into a completely safe, open foraging arena for the seals. With the regulatory pressure of the shark removed, the behavioural matrix of the Cape fur seal population undergoes an immediate and radical shift, initiating a classic top-down trophic cascade. Without the fear of shark attacks, the seals completely abandon their cautious, energy-taxing vigilance strategies. They no longer restrict their movements to specific paths or travel in protective groups. Instead, they distribute themselves widely and continuously across the entire coastal ecosystem, foraging with total freedom. This complete behavioural liberation leads to a dramatic spike in foraging efficiency, which quickly translates into a major population boom. While a thriving seal population might initially appear to be a positive indicator of environmental health, from a systemic perspective, an unregulated population of mid-level predators is an ecological disaster. An adult Cape fur seal is a highly efficient carnivore, requiring vast quantities of fish, squid and crustaceans every single day to sustain its high mammalian metabolism. As thousands of seals forage without fear across the unguarded bays, they apply an unprecedented level of predatory pressure on the lower levels of the food web. The first major environmental casualty of this unregulated seal activity is the commercial fish stock of the region. The seals consume massive quantities of small pelagic fishes, including sardines and anchovies, as well as high-value demersal species like hake. As the seal population expands exponentially, their aggregate consumption outpaces the natural reproductive rates of the fish stocks, leading to a sudden, severe depletion of local fish populations. This decline directly harms the local artisanal and commercial fishing economies, but its most devastating impact occurs within the native marine bird communities. The most critical environmental crisis triggered by this trophic cascade involves the endangered African penguin, scientifically classified as Spheniscus demersus. The African penguin relies entirely on the exact same small pelagic fish species, sardines and anchovies, to feed itself and nourish its vulnerable chicks. Under the original ecological balance, the great white sharks indirectly protected the penguins by keeping the seals concentrated near their breeding islands, leaving the open coastal waters rich with fish for the birds. With the sharks gone and the seals roaming freely, the penguins find themselves completely outcompeted in a depleted ocean. Individual penguins are forced to swim significantly further out to sea, expending precious metabolic energy to locate increasingly rare schools of fish. Many adult penguins return to their nesting colonies entirely empty-handed, leading to widespread starvation and catastrophic reproductive failure among penguin chicks. Furthermore, the environmental pressure on the penguins is doubled by direct seal predation. Cape fur seals are highly opportunistic hunters. When their primary fish resources begin to decline due to their own overexploitation, the seals transition their hunting focus to the penguin colonies themselves. Raiding parties of young male seals patrol the shallow waters directly in front of the penguin nesting beaches, intercepting and killing thousands of adult penguins simply to consume their fat-rich stomachs. For a species that is already hovering on the brink of extinction, this sudden, dramatic surge in seal predation, directly caused by the absence of the great white shark, represents an existential threat that could completely wipe out native penguin colonies within a generation. Simultaneously, the trophic cascade reshapes the physical architecture of the coastal environment by damaging the local kelp forests. Kelp forests, composed of giant structural algae, serve as critical nurseries for hundreds of species of marine life, dampening powerful ocean waves and storing vast amounts of carbon. These delicate underwater forests are maintained by a complex balance of predatory fish, sea urchins, and smaller marine organisms. As the massive population of unfeared seals overconsumes the local predatory fish and octopuses that inhabit the kelp, the populations of herbivorous invertebrates, like sea urchins, expand without check. These urchins graze destructively on the holdfasts of the giant kelp, severing the algae from the seafloor and transforming lush, three-dimensional underwater habitats into barren rocky deserts devoid of biodiversity. Through this complex web of cause and effect, the science of the landscape of fear becomes undeniably clear. The fear of the great white shark was the primary regulatory glue that held the entire South African marine ecosystem together. The surgical efficiency of a single pair of killer whales, by driving the ocean's largest predatory fish into deep-sea exile, completely pulled the plug on this ancient stabilizing mechanism. The resulting trophic cascade proves that an apex predator does not just balance an ecosystem through the animals it physically eats. Its true power lies in the wide structural shadow of terror it casts across the environment, an invisible shield of fear that protects hundreds of species and maintains the vital biological integrity of the global ocean. As the long-term absence of the great white shark continues to destabilize the coastal marine ecosystem, nature begins to fill the vacant ecological space through a process known in evolutionary biology as ecological niche displacement. An ecological niche is not a physical location, but a functional role within a habitat, encompassing an organism's specific trophic relationships, resource utilization, and predatory duties. When a dominant apex predator is completely removed from its functional position, it leaves behind a massive resource-rich void. In the waters of South Africa, alternative marine predators have stepped forward to claim this open territory, most notably a smaller cartilaginous species known as the bronze whaler shark, or copper shark, scientifically classified as Carcharodon brachyurus. Historically, bronze whaler sharks were heavily restricted in their spatial and temporal movements within bays like Gans Bay and False Bay. Measuring up to 3.3 meters in length and weighing around 250 kilograms, the bronze whaler is a formidable predator in its own right, yet it sits a full trophic step below the great white shark. Under the original ecological balance, bronze whalers maintained a highly cautious lifestyle, actively avoiding the prime seal hunting channels because adult great white sharks would not hesitate to kill and consume them as competitors. With the great white sharks driven into deep-sea exile by the fear of orcas, the bronze whalers experienced an immediate release from this predatory suppression. Telemetry data and visual surveys recorded a massive influx of bronze whaler sharks into the shallow coastal zones, formerly dominated by Carcharodon carcharias. They began aggregate patrolling around the Cape Fur seal colonies, attempting to assume the role of the primary regulatory predator. However, this niche displacement has revealed a critical evolutionary lesson. A smaller, cold-blooded generalist predator cannot truly replicate the profound ecosystem stabilizing effects of a genuine 5-meter apex specialist. While bronze whalers are highly efficient at hunting schools of fish and smaller squid, their smaller jaw architecture and lower mechanical bite forces make it highly difficult for them to successfully hunt large, aggressive adult male fur seals. As a result, their presence has failed to re-establish the intense landscape of fear necessary to control the behavioral freedom of the seal population, allowing the destructive top-down trophic cascade we analysed previously to continue almost completely unabated. More tragically for the bronze whalers, by stepping into the vacant niche of the great white shark, they unknowingly place themselves directly in the crosshairs of the ocean's true mammalian rulers. In a stunning display of behavioural adaptability, Port and Starboard quickly recognised this ecological shift. Realising that their primary target had vanished, the two orcas adjusted their hunting focus to the newly arrived bronze whaler sharks. Because bronze whalers are smaller and possess an entirely cartilaginous skeleton that is even more flexible than a great white's, they are even more vulnerable to the hydromechanical inversion tactics and tonic immobility tricks used by the killer whales. Within a short period, marine scientists began discovering the carcasses of bronze whaler sharks washing ashore on South African beaches, bearing the identical surgically precise horizontal tear between the pectoral fins and the total absence of the lipid-rich liver. The mammalian intellect had simply adapted to the changing ecosystem, proving that no matter which shark species attempts to claim the throne, the crown of the ocean remains firmly in the possession of the cetaceans. This absolute dominance of marine mammals over cartilaginous fishes is not a temporary modern anomaly. It represents the latest chapter in an epic multi-million-year evolutionary arms race that has shaped the biological history of the global ocean. To truly understand this structural rivalry, we must journey back into deep geological time, tracing the evolutionary pathways of the classes Chondrichthyes and Mammalia. Sharks are an incredibly ancient lineage of life, having patrolled the Earth's oceans for over 400 million years. They survived the Permian-Triassic extinction event, outlasted the dinosaurs, and perfected a physiological blueprint based on cartilage. Passive bioelectric sensors and cold-blooded or regionally endothermic metabolisms long before the first mammals ever entered the water. For hundreds of millions of years, this cartilaginous design held an absolute monopoly over high-level marine predation. However, approximately 50 million years ago, a massive evolutionary pivot occurred during the Eocene epoch. A group of terrestrial, four-legged mammalian artiodactyls began a profound transition back into the aquatic medium, giving rise to the first primitive cetaceans known as archaeocetes. These early marine mammals brought with them a completely radical suite of biological innovations developed on land: a highly efficient, warm-blooded mammalian metabolism, a large, deeply folded cerebral cortex capable of complex learning, an oxygen-rich respiratory system supported by high-capacity lungs, and a skeletal system made of true mineralized bone. As these cetacean lineages expanded throughout the global ocean, they inevitably locked into a direct, violent evolutionary confrontation with the reigning giant sharks of the ancient world. The peak of this historical arms race occurred during the Miocene and Pliocene epochs, approximately 15 to 3 million years ago. During this period, the global oceans were dominated by two of the most terrifying macropredators to ever exist: the legendary megatooth shark, Otodus megalodon, and a massive predatory sperm whale known scientifically as Leviathan melvillei. Megalodon was a colossal biological machine, reaching lengths exceeding 15 meters and possessing a cartilaginous jaw capable of exerting a crushing force of over 180,000 newtons. Leviathan, conversely, was a highly advanced mammalian heavyweight, measuring up to 17 meters in length and equipped with massive, deeply rooted, bony teeth designed to crush and tear the flesh of other large whales. These two giants competed directly for the exact same resource: the high-fat, energy-dense blubber of primitive baleen whales. The ultimate outcome of this ancient Miocene arms race was not decided by raw physical size or jaw power, but by climate change and cognitive scalability. As the global climate shifted during the Pliocene epoch, entering a period of significant cooling, the distribution and migration patterns of baleen whales altered dramatically. The warm-blooded marine mammals, possessing superior internal homeostatic control, advanced social communication arrays, and the ability to coordinate complex group hunting strategies over vast geographic distances, were able to track these changing prey movements with absolute efficiency. The solitary, cold-blooded or partially endothermic giant sharks, locked into rigid instinctual behavioral matrices and lacking a mechanism to transmit tactical data or cooperate across generations, could not adapt to the changing oceanic conditions. Megalodon eventually fell into extinction, leaving behind a vacant global niche that would eventually be claimed by the ancestors of the modern great white shark. Simultaneously, the predatory cetacean lineages continued to evolve, maximizing their neurological complexity, refining their active acoustic echolocation lenses, and organizing into highly structured multi-generational pod systems. The modern supremacy of the killer whale over the great white shark is the direct logical culmination of this ancient evolutionary trajectory. It is a profound historical proof that while raw physical power and ancient sensory perfection can maintain a kingdom for millions of years, it is the evolution of collective intelligence, real-time strategy, and mammalian adaptability that ultimately wins the war for the global ocean. Our comprehensive scientific investigation across anatomy, behavioral ecology, biochemistry, and marine telemetry brings us to an undeniable ecological conclusion. The traditional view of the ocean's food chain, long dominated by the terrifying silhouette of the great white shark, has been thoroughly dismantled by empirical data. The true apex ruler of the global ocean is not a solitary ancient fish, but a highly advanced, socially complex marine mammal. Carcharodon carcharias remains an absolute masterpiece of evolutionary engineering, equipped with 18,000 newtons of jaw force and unmatched bioelectric arrays. Yet, when confronted by Orcinus Orca, the shark's entire biological blueprint is completely outclassed. The killer whale operates on an entirely different evolutionary plane, weaponizing its heavy bone skeleton, massive jaw forces, and medical-grade acoustic echolocation to locate and neutralize its target before the fish even registers a threat. More importantly, the true crown of the orca is its magnificent, highly folded brain. By organizing into multi-generational matriarchal pods, developing distinct cultural dialects, and communicating in real time, these cetaceans do not just hunt, they execute calculated, multi-stage tactical operations. They have successfully mapped the physiological vulnerabilities of their ancient rivals, using hydromechanical physics to trigger tonic immobility and surgically tricking the calorie-dense, squalene-rich liver with absolute precision. The resulting landscape of fear and wide-reaching trophic cascades prove that the balance of our entire marine ecosystem is held together by the strategic choices of these intelligent mammalian sovereigns. The ocean remains a vast, dynamic frontier of scientific discovery, where ancient instincts continuously clash with collective intelligence. Thank you for joining us on this deep-sea scientific documentary. If you found these breakthroughs insightful, please support our ongoing research content by hitting the like button and subscribing to our channel. Before we close our logs for today, please join our global scientific community by leaving a comment down below sharing the exact geographical location and the local time from which you are watching this broadcast right now. Until our next subaquatic expedition, keep exploring the wonders of our natural world